Hello everyone. Let's talk about the heaps in this video. Yet another kind of this data structure. We're gonna see both max heaps and min heaps. Here are two examples of max heaps and min heaps, but let's see what it is. What's a heap? So a heap itself is a binary tree. As you see, both examples are binary trees in which the very first node, which we call the root, has a special has a specific feature. If it is a max heap, then the root has the highest value. If the heap is a min heap, the root always has the smallest value. Plus that if it is a max heap, every node has smaller value compared to its children. And if it's a min heap, if it's a max heap, each node has higher value to its children. So max heap, higher value compared to children. Min heap, smaller value compared to its children, as you see in this example. So 10 is the root in the max heap, and 5 and 6 are smaller. And also you see 5 and 6 are the parents of 2, 4, and 3, and 1. Each of them also has higher values compared to its children. The min heap here on the right side, we have number 1, or the key 1 at the root, which is the smallest number, and then we have the 2 and 3 as the children of the node 1. Both of them also has higher value compared to 1. Also, they have smaller value compared to their children, which are 4 and 6 for the 2, and 5 and 10 for the node 3. So here at the bottom of these trees, you see two arrays, which is another way of representing a heap. So you can start from like the top down and top down left to right approach to write all the numbers or the keys or the items in the array. So in order to traverse or show the items of a heap into an array, we can actually use the breadth first traversal that you can watch in my other videos of how to do that. So here again, top down and left to right representation or traversal of a tree will create the array representation of a heap. So you might ask, okay, what is the the use of like heaps? Well, we were trying to keep like the very first numbers or the very first node to be either the maximum or the minimum. So we know that at any point with the time complexity of big O 1, we can access to the root, because that's the only node that usually when we're implementing a tree, we have access to it at any point. So it's good just to implement, if you want to implement the priority queues in which that the task or the the items with the higher priority will needs to be processed. So here I'm going to show some other features and properties of a heap. So if you look at this array representation, and let's choose any index. So let me also write the indices here. So we're assuming that indices are starting at 0. So 4, 5, and 6. So there are 7 items in this 3, 0, 1, 2, 3, 4, 5, and 6. So one feature if you use an array in order to show the heap rather than a tree is that the parent of each node is at index I minus 1 divided by 2. So here you can just select you can use the floor. So the parent index is at index I minus 1 divided by 2. For example, if you look at the number 1, which is at index 6, its parent is number 6, as you see here. So this is the node 1, and as you see, its parent is the node 6, which is at index 2 when we show it in the array. So I is 6, and again, I is the index of the node that we're trying to find its parent. So for 6, the node 6, 6 minus 1 is 5. 5 divided by 2, and again we're using the floor. That's going to be equal to 2, which is exactly the index 2 with the value 6 that we're looking for. Another example here going to be 3, which is parent also is 6, and is at index 5. So 5 minus 1 and getting the floor when dividing by 2, that's going to be also 2, which means the like the node 3 also has the parent of like the 6. Here the same example, or similar you can see that here the node 6, which is index 4, and know that its parent is index 1. So how we did that one, 6 is at index 4 minus 1 and get the floor when divided by 2. So it's going to be again floor of dividing 3 by 2, which is going to be equal to 1. And again the floor, if you don't know what the floor is the largest integer number which is less than the number. So 3 divided by 2 is 1.5, and the largest number integer number that is smaller than that number is number 1. So that's the meaning of the floor, like the function in math, or floor concept in math. So one other good interesting feature of a heap is that, as you see also in my examples, they are balanced. So that means that the height of the tree is at its minimum possibility. So here we have 7 nodes and we have perfect complete binary trees. Both of them have exactly 7 nodes, so a complete binary tree of height 3, and we'll learn about this one. So you can again watch my other videos about trees and also complete binary trees. So that was about the parent index. So what about the left or right child of a node, if exists at all? Okay, so the only node that doesn't have any parents for sure is the root, and it's gonna, when you put 0 here, it's gonna be a negative number, so that does not exist because the indices start at 0 in the based on what we wrote here. So the left child index, so left child index will be at index 2 times I plus 1, and the right child index will be at index 2 times I plus 2. Again, you can just easily verify that. For example, node 5 has the nodes 2 and 4 as the children, so it's index 1. So 2 times 1 plus 1, which is going to be 3, is the index of left child, which is 2. Here is correct. And then 2 times 1 plus 2 is 4, which is the index of its right child, which is correct because index 4 has the value 4, which is correct. If you look at this one and this min-heap here, for example, the node 3, which is at index 2, so its left child is at again 2 times 2 plus 1, which is 5. So index 5, which is number 5, also is its left child, and 2 times 2 plus 2, which is 6, and as you see here is number 10 is its right child. So these are about like the very basic of the max heap also and the min heap. So you might ask how we can actually insert numbers into a heap. So let's assume that we have a few numbers. So for example, number 10, 15, 8, 7, 2, 6, 1, and 3, and then also 4. And let's say we're going to insert these numbers into both a max heap and also a min heap. So I'm going to explain how to create a heap using the numbers in when we are inserting numbers one by one. So in order to do that, we're going to start with the very first numbers, for sure from the left or from the order that we receive the numbers, and I'm going to start with the max heap example first. So we're going to put 10 to be the root, and that's the only node that we have here. After that, the number that we see is 15. So because we want to make sure that the heap is always balanced, we're gonna just put it to the very left side. So we always start from the next level. If it has any spot available, we're gonna put it, and we're gonna start from the very leftmost node available. So the very leftmost available here in this case is the left child of 10. So we're gonna put 15 to be the left child of 10. Because we wanted to create a max heap, number 10 is not the maximum number anymore. We have two nodes and we have number 15. So what's going to happen, we need to actually swap the values of 15 and 10. So anytime that we're inserting a new node, we need to look up and check with all of its parents and make sure that if they need to be swapped, we need to swap the values. So after checking, because 15 has a higher value compared to its parent, which is 10, we need to swap the values, and we're going to have 15 and 10. So after inserting number 15, that's going to be the actual heap that we're going to create. After that, we have number 8. So we're going to insert number 8 at the very leftmost, but the next level. So number 10 is on the left child, so the only spot available in this level is the right child of 15, so it's going to be 8. And because 8 is smaller than 15, so we're not going to swap the values. And again, we only care about the root that always has the maximum number. If it's a max heap or a minimum number, it's a min heap. Although again, that's the rule that every parent also must have a higher value compared to its children in a max heap, smaller in a min heap. Next number we're going to insert is 7. So 7, again, we're going to go to the very leftmost of the next level, because now we are done with this level here, 10 and 8. So number 7 will be inserted here. And as you see, 7 is smaller than 10, so we don't need to even check with the grandparent of 7, which is 15, because we already know that 7 is less than number 10. So the next number is 2, which will go to the next spot in this level, which is going to be 2 here. And again, 2 is smaller than 10, so we're done. We should be careful. We don't care about the siblings here. We just want to make sure that they have smaller values compared to its parent. And after number 2, the next number is 6, which is going to be the left child of 8, and 6 is smaller than 8, so we're good. The next number is 1, which is smaller than, again, 8, so without any problem, we're going to insert 1 here. Then after number 1, we have number 3, which is going to go to the left child of 7, and again, there is no need to change. And then after that, we have number 4 without any problem. And here we have a max heap, and as you see, number 15 is on the at the very first node with the root, and every node has a higher value compared to its children, and the tree also is balanced because that's the way that we are inserting the node into the heap. So that was an example of creating a max heap with these numbers, and as you see, we only had to do one time swap when we inserted number 15 after number 10. So let's see that how we can actually create a min heap with these numbers provided here. We're starting with 10 again, so that was our max heap example, and then here we have the min heap example. So starting with 10, and then after that we're going to insert number 15. So it's to the left, and as you see, 15 is greater than 10, so 10 must stay at its place because 10 is the minimum number so far. After that, we're going to insert number 8. However, because it's a min heap, 8 is not greater than 10, so we need to swap the values of 8 and 10. So what's going to happen? We're going to have 8 here, and then 15 and number 10 will be on there as the right child. After that, we have 7, which is going to go to the next empty spot. Again, starting from the very leftmost, which is going to be the left child of 15, which is now going to be 7. So we're going to compare 7 again. We're going to look up because 7 is smaller than 15. We need to do one time swapping, so it's going to be 8. Then we're going to have 7, and here we're going to have 15, and here is gonna go number 10. Again, we need to go up and check. So because 7 has a smaller value compared to 7, we're gonna do one more time swapping. So 7, and then 8, and then here we have 10, and we here have number 15. So that's the, as you see that we by inserting number 7, we had to do the swapping function or action twice. After 7, we have number 2, which we're gonna be again starting from the leftmost. 15 is occupied the left side, and now the right child of 8 is empty. So we're gonna insert number 2. 2 has a smaller value compared to its parent, which is 8. So we're gonna swap. So it's gonna be 7, and then here we're gonna have 2, and then number 15 on the left child, and here we're gonna have number 8. And it's number 10 will still stay at its proper location. So again, 2 is smaller than 7. We need to one more time swapping. So to put 2 at its proper location, 2, and then 7, and then here we have 8, and here we have 15, and here also we have number 10. After number 2, now we have number 6. So that's gonna be the very left child of 10, because again here is auto occupied. So number 6, and 6 is smaller than 10, so we need to swap the values 6 and 10. So 2, and then here we're going to have 6, so 10 will be now the left child of 6. We're going to have 7, and then 15 here, and then here we're going to have 8. After number 6, we have number 1, which is going to be the right child of 6, because that's the only spot in this row available to insert. So number 1 is less than 6 and also less than 2. We need to do the swapping twice. So what I'm going to do here, I'm going to show that 2, and then number 1, and then number 6 here, and then number 10 here, number 7, number 8, and number 15 are here. 1 is smaller than 2, so we need to swap. So 1, and then here we have 2, and here 6, and here 10, 7, and 8, and 15. So we also inserted number 1. Then we have number 3 and numbers 3 and 4. So number 3 will be the left child of 15, because we're done with the third level. So 1, 7, and then 2, and then 15, then 8, then 10, 6, and here we have 3. So because 3 has a smaller value compared to 15 and 7, we need to swap. For sure we will stop when it reaches number 1, because 1 is smaller than 3 and is not larger than that. So we're gonna have 1, then here we're gonna have 7, and then we're gonna have 2, and this 6 and 10, and here we're gonna have 3, here we have 8, and here we have number 15. So although I could just maybe skip some step, I just want to show you the whole process. That's what actually happens. So here we're going to have 1, then here we have 3, and then here we have 7, 8, and 2. Again, we are just swap the values of 3 and 7. That's the whole thing, or everything that we did so far. So 6, and then we have number 15, and after that we have number 4, which is going to be the right child of now 7. And again, 4 is smaller than 7, so we need to do one swapping here as well. We have 1, then we have 3 and 2 on the right child, then we're going to have 4, and then here we're going to have 7, and then it's going to have 15, and here's going to be I think number here is going to be 8, and that's going to be actually number 10 and not 8. So let me fix this one. So 10, and here is number 6. So I think we're done. As you see, each node has a smaller value compared to its children. 4 and 2 and 3, both all of them has smaller values compared to its children. Also number 1 is the minimum number. So that's the min-heap representation, or the way that insertion works in a min-heap. As you see, if you insert one by one all the numbers, if you have or if you have an existing heap and you want to insert a new item, that's how it works. So one by one, that's the min-heap, and here was the representation of the max heap. Maybe it's better if I just put them all together. So here's the let me maybe put the try around here. So that's our max heap, and here is our the min heap. So all together, so just for a comparison. So again, I just showed all the steps for sure, but if at the end what we care is the final state of a max heap, and these are the intermediate steps in order to build or fix the heap as soon as it just becomes not a heap anymore. So we need just do these steps. So that's about the insertion, and now we're going to also learn about the deleting from a heap. So let's look at this example that we just created, the min heap, and we're going to see that how we can just do the delete or just delete the nodes in heaps. So in heaps we only delete the root node, and again, because that's how the heaps are defined, because they are going to be used for because of their specific feature of having the minimum value at the root or the maximum value at the root. So it makes sense only to delete or remove the root node. So, and we're gonna make sure that the heap after removing the root node still is balanced, and it's gonna be heap, means that it should contain its features. If it's a main heap, smaller than its children, and also again being balanced. So in this tree that we have here in heap that here, I'm going to show you how to delete the root, which is 1. So in order to do that, we're keeping the data of the root at some temporary variables. For example, if you want to return it, and then we are choosing the very last node of the tree, which is, in the example I have here, is the node 6. The node actually is the node not 6 but node 7. So maybe I just tried a little bit bad maybe. So the node 7, which is in the last level. So here is the level. So here's one, and the other one. Here's another one. As you see, 7 is the last child and the last node of the heap. So here we're going to swap, not swap, we're going to replace the value of the root with 7. So again, we're keeping the value of 1 in some temporary variable in order if to when I'd like to process them later, or when I return the value to other places. But here what's going to happen. So we're going to replace value of 7 with 1, and we're going to delete the node 7. So 7 going to sit here, and then here is going to be 3, and then 2, and then 4, and then 8, and then here we have 10, and here we have 6, and here we have 15. So as you see here, the reason that we just use the node 7 because we wanted to keep the tree still balanced, and that's the case by now. However, there is a problem. Number 7, or the key 7, is not the minimum item of this heap anymore. So exactly in the opposite way that we inserted. So in the insert we were looking up after inserting, but after deleting the root, removing the root, we're going to look down and just go down to make sure that the root is actually the minimum number. So that's how it works. So when you're replacing the last node with the root, we need to compare its value with its immediate children, which are number 2, or the nodes with the keys 2 and key 3. Between these two, 2 is smaller, so we're gonna swap the values of 7 and 2. So we're gonna have 2, and then here we have 3, and here we have again 7 because we swap, and then here we have 10, and here we have 6, and here we have 4, and here we have 8, and here in the last level we have number 15. So, and as you see here already, number 2, which is the minimum number, is actually at the very root of or the very first node of the tree. And you want to ask why this has happened, because again, that's a hierarchy, or like it is a pattern that repeats in the whole heap, that each child must have exact smaller value compared to its children. So 2 has a smaller value compared to its descendant. That's why it's now, when it's on the very top of the tree, is actually the minimum number. So now again, we need to just check, look down, and we need to stop if it's not smaller. But between 7 and 6 and 10, so when comparing, we know that 6, which is right child of 7, has a smaller value. So we need to do the swapping one more time. So we have 2, and then here we have 6, which is swapped with 7. So here is 7. Here we have 10, and here we have 3. Here we have 8. Here we have 4, and here we have 15. So here is the heap after removing the root, which was number 1, and now the 2 is at the root. So what I'm going to do, I'm going to just show one more example of the deleting, and here we're going to use again the same tree that we had. So the last node in this heap that we have is number 15. So we're going to remove the root, which is number 2. We're going to again replace the value of 2 with 15. So 15 will go to be the very root, and then here we have 6, and then here we have 7, and here we have 10, 3, and then 4, and then here we have 8. But as you see here, 15 is not the smallest number. So we need to just go look down. Again, this example I'm writing is for a min-heap. If it's a max heap, we actually need to make sure that the root has the highest value. So that's exactly, you're gonna the way you compare will be different. If it's max heap, you're looking for the max heap, you're looking for the maximum number. If it's a min heap, you're looking for the smallest number. So between 15, 3, and 6, the 3 is the smallest. So we're gonna put the 3 to be the root. No change for sure on the right side, because we didn't pick number 6. And here we're gonna have 15, and then here we have 8, and here we have 4. So still we need to look down, because 15 is not smaller than its children. So between 15, 4, and 8, 4 is the smallest. So we're gonna swap the value 4 and 15. So 4 here, and then here we're gonna have 15. You're gonna have 8, and here's gonna be 6, and it's gonna be 10, and here is gonna be number 7. So that's what we need to do in order to do the insertion and like the deletion of the heaps. So you might say that what's going to be the time complexity in order to do the insertion. So if we have n numbers, so for sure we have n n operation so far, or n something related to n, because there are n numbers, and we're going to see that what's going to be the time complexity to insert any node. Okay, so that's n nodes. They're going to be inserted. What is the time complexity for insert n nodes? As you see here, we're dealing with a balanced tree, which is very close, or a tree that very close to the complete binary tree. And we know that the height of the binary tree is log of n, and that's exactly how much we need to go down. Okay, anytime we're inserting a new node, we're going to insert it as the very last node of the tree, and the very last node of this almost complete binary tree is at the very bottom of the tree, which is at the height of log of n. So in order to insert n nodes in a heap, okay, we need to do n log n, or like the big O, or the time complexity from the n log n. Again, log of n is the height of the tree, and n is the number of nodes that we're going to insert, so together it's going to have n log n. Again, that's not the exact number of operations, but is the degree or the order of the time complexity for the this process. Also, the time complexity in order to remove the root is log of n, because if we remove the root, we need to replace its value with the the node at the very bottom of the like the tree, which is the last node, and it's gonna take at maximum log of n if we need to do any swapping. So maybe swapping the node that was here. If we go to this example one more time, so here we had to for example number 2 had to be swapped with 7, and here again we had to swap with 7 with 6. So as you see, it goes to the very bottom of the tree, which is at maximum is log of n. So if we're going to remove only one node, it's going to take only log of n. We're going to remove all the nodes, but one by one, it's going to take n log n, because again we have n nodes, and for each of them going to take n log n. Again, that's a degree of the like the time complexity for the insertion and deletion. Insertion is going to be n log n for inserting n nodes, and removing one node at a time going to take log of